Hey, welcome to GP Podcast. In the world of computing, there are names we all know, but what about the ones that operate in the shadows?
Think about it. You could probably explain what a CPU is, right? Maybe even a GPU. But the Tensor Processing Unit, the TPU, for most people, that's where the map goes blank. While CPUs and GPUs are the familiar, everyday workhorses, the TPU is something else entirely. It's a specialist, a secret weapon really, built for a very specific kind of war. And today, we're going to pull back the curtain and uncover its secrets.
All right, here's our roadmap. First, we'll tackle the massive problem that even created the need for something new. Then we'll look at why the old guards, CPUs and GPUs, just couldn't keep up. That's when we meet the hero of our story, the TPU. We'll crack open its biggest secret, see how it scales up to become a monster supercomputer, and finally, get our heads around the unique philosophy that makes it all tick. So to really get the TPU, you first have to appreciate the beast it was designed to fight. Because modern AI, especially deep learning, well, it's not some delicate art form. Nope, it's an act of pure, brute force computation.
Just try to imagine training a huge language model. What's actually happening? It's a relentless storm of math, specifically massive matrix multiplications. We're talking about these huge multi-dimensional grids of numbers called tensors. Think of a spreadsheet, but with thousands of tabs all being crunched at once. This insane computational hunger is the exact thing that our traditional hardware just wasn't ready to handle.
So the obvious question is, why couldn't we just use the tools we already had? We had powerful processors. Let's take a quick look at the old guard and see exactly where the cracks started to show.
On one side, you've got your CPU. It's the ultimate generalist, a real jack-of-all-trades. It's great at juggling a million different tasks one by one, which is perfect for your laptop. But for the sheer parallel madness of AI math, way too slow. Then you have the GPU. Now this thing is a parallel powerhouse for sure, but it was born to render graphics, which means it's still built with a lot of flexibility that AI doesn't necessarily need. And this is where it gets really interesting. For these pure AI jobs, a GPU's greatest strength, its flexibility, actually becomes a weakness. A whole bunch of its specialized hardware, stuff like texture units, just sits there, doing nothing. A lot of the silicon is literally wasted if all you care about is deep learning. It's like using an incredibly complex Swiss Army knife when what you really desperately need is a power drill.
So, the problem was clear. The demand for computation was exploding, and the existing tools, powerful as they were just not the right fit. The stage was set for something new, a new kind of processor, built from the ground up for one single monumental purpose.
And here it is, the Tensor Processing Unit. It's what's called an ASIC, an application-specific circuit. That means it was designed from day one to do one thing and one thing only: tear through those massive tensor operations at the heart of AI. It just strips away all the extra fluff you'd find on a GPU, dedicating its entire existence to raw mathematical throughput.
Now, this is absolutely crucial to understanding the TPU mindset. It doesn't really care how fast it finishes one single little calculation, not at all. What it cares about is how many trillions of calculations it can finish every single second. It's all about volume, about throughput. It's designed to be a fire hose of computation for training and inference, always maximizing the total number of operations.
Okay, so how on earth does it achieve that mind-boggling volume? We're about to get into the really cool part. This is the core innovation, the architectural trick that gives the TPU its superpowers. This is the secret weapon. I want you to forget everything you think you know about how a processor works. At the heart of a TPU is something called a systolic array. It's not a processor in the traditional sense. It's a physical grid. A checkerboard of thousands and thousands of tiny, simple calculators, all wired together to perform matrix math in this rhythmic, pulsing, wave-like fashion. So here's how this beautiful dance works. Data, like a neural network's weights, streams into the grid from one direction. Other data, like neuron activations, streams in from the top. As these waves of data meet on the grid, each little calculator does one simple thing. It multiplies and adds. Then it passes the result to its neighbor. The calculations literally cascade across the array, like ripples in a pond, and the final answers just pour out the other side. It is a perfectly synchronized assembly line just for math.
And the advantage here is just profound. This design tackles the single biggest bottleneck in computing history, having to constantly go and fetch data from main memory. It's slow and it burns a ton of power. But by keeping the data constantly flowing and being reused inside the array, the TPU completely sidesteps that ancient problem. The result? unbelievable efficiency and a massive leap in performance per watt.
All right, so one of these TPU chips is an absolute beast, but the AI models we're building today are so colossal that one chip isn't enough. You need an entire army, all working in perfect harmony. So let's see how they get assembled into a true supercomputer.
You have to think about this like you're building an entire city from scratch, a city dedicated only to AI. You start with what's called a cube of 64 chips all interconnected. That's your first city block. Then you group those blocks into flexible slices. Those are your neighborhoods. And finally, you link all the neighborhoods together with a high-speed network to form a pod, an entire massive city built to train world-changing models like Gemini.
And to give you a sense of that scale, a single TPU v4 pod connects 4,096 of these individual chips. And we're not just talking about a bunch of computers sitting in the same room. No, these things are woven together. They're designed from the ground up to act as one single entity. The magic that ties this whole city together is a custom-built, ridiculously fast network. These special interconnects let all 4,000 chips talk to each other at lightning speed, making the whole pod function like one giant, cohesive brain. And that kind of teamwork is the only way you can train the biggest AI models on the planet.
Okay, for our final piece of the puzzle, let's talk about the philosophy behind the TPU. Because this is about more than just clever hardware. It's a fundamentally different way of thinking about how computing should be done.
So here's the big shift. A normal CPU or GPU uses what's called dynamic scheduling. That means the hardware itself is constantly making decisions on the fly, predicting what to do next, figuring out what data to keep handy. It's flexible, but it's also really complex and eats up power. The TPU, it does the opposite. It uses static scheduling. A very smart piece of software, a compiler, plans out every single operation, every single step, long before the hardware even sees it. And the payoff for this teamwork between hardware and software, well, it's the whole point of the TPU. By letting the software do all the heavy thinking up front, the hardware itself can be radically simpler and way more efficient. You don't need all that complex circuitry for prediction or caching, and all that physical space you save on the chip, you can fill it with what really matters. More of those math-crunching systolic arrays. That is the essence of the TPU right there. You trade away general-purpose flexibility for a staggering leap in performance on the one task that truly defines modern AI.
And that leaves us with one final, really provocative thought. The TPU is definitive proof that if you design hardware for one very specific problem, you can achieve performance that a general-purpose chip could only dream of. So as our computational needs in all sorts of fields get more and more specific, is this the future? A world not of one-size-fits-all processors, but of countless hyper-focused specialists? If you liked the video, subscribe, leave a like, comment on what you liked most, and share the video.